Hello, calculus friends. Welcome to section 2.4, where we take a little break from the hardcore limits we've been working on, and we're going to take a break and just talk about continuity. So this is all about continuity, and sort of the little visual that you see up here with the line going through continuity. Isn't that cute? Mr. Brown, you're so clever. Oh, stop. You're too kind. But basically, continuity just means, as you see here, can you draw a graph without having to pick up your pen or pencil? Meaning, as I just trace my pen along, I'm not picking up my pen or pencil, so this graph is continuous. But if I pick it up and I start over here and I go over here, you can see there's breaks in my graph, so it's not continuous. So for a graph to be continuous, it's kind of a crude description, but it's just very easy to think about it as, can you draw it without picking up your pen or pencil? All right, but we're in calculus, so we have to put a calculus definition. Ready? Here we go, friends. A function is officially continuous at a number, like a, if, and this is big, if the limit as you approach a, and that means from the right and from the left, the limit is the same thing as if you actually plugged in the a value and you got the same y value. If the limit actually literally equals the dot on the graph. Okay, so I'm going to show you a lot of examples where that doesn't work, but let me just re-emphasize it with three huge parts here. All right, continuity always has three parts to our club. Ready? To be part of the continuity club, three things need to happen. Ready? Part one. That means the limit has to exist. In order for it to be continuous, the overall limit as you approach that number a, the limit has to exist. And that means, again, from the left and from the right. So you've checked both sides. If the limit exists, check. Okay, well, on the graph, does the point actually exist? Is there an actual dot at A? Do you get an actual y value versus, if there's like a hole, which we don't like. So if there's an actual dot on the graph at x equals A, great. And the most important thing, the thing that unites them together is the answer for number 1 up above equal to the answer to number 2? Meaning, is the limit equal to the y point? So does 1 equal 2? Does the limit exist? Does the point exist? Are they the same? And if so, man, that graph is totally continuous at that point. So check and see. Here's a really good diagram to help you out. So here's our a value down here, friends. As I approach a from the left and from the right, let's check and see. We're going to analyze right now, is this graph continuous at this yellow point right here? So let's do each one. All right, part one. Does the limit exist from the left and the right? And as you wander around, you approach a really closely, you get that value, f of a we call it. As I approach from the right-hand side, I also get f of a. So does the limit exist? Check. All right. Part two just says, does the point exist? As you see, as I plug in a, is there a dot or is it an open circle? It's a dot. So, does the point exist? Yes, there is a dot. And here's the important part. The last part is part 3. Is the point equal to the limit? So the limit was this y value, and the point is this y value. Are they the same? Oh, you betcha. So is it continuous? Yay! Commence your applause. So that's really important. So put down all 3 steps here, especially on the AP. They will ask, can you show that this is continuous? And you'll have to show all 3 things. You're going to show, first of all, does the limit exist? Left and right side. Does the point exist? And did you get the same answers for step 1 and step 2? Okay, so that's continuity. 3 big calculus steps. So here's where you get a chance to practice, guys. In your notes right now, I want to ask for you to be creative. I want you to draw your own graph, depending on 3 different conditions. So, if we were in the classroom, I'd have you come up to the board. So sorry. So we can't do that today. But just go ahead in your notes right now. I want you to draw each one of these, one at a time. Graph number 1. I want you to draw a graph for me where the limit exists at x equals a from the left and right, but the function is not defined at a. Try to think about what that means. The limit exists coming from the left and the right, but the function is not defined. Think about the point not existing. Okay, for number 2, I want you to try this graph separately. I want you to say the function is defined at a, means the point's there, we're good, but the limit doesn't exist. Ooh, interesting. What's that going to look like? And finally, number 3, can you draw a graph where the limit exists left and right. The function exists, but the two answers are not the same. Ooh, hoo, hoo. Good luck on that. So pause this video, friends. Try each of these graphs, and we'll check and we'll see how you do. Good luck. All right, I'm actually going to put all three graphs together at once. I wonder if you can see. So the first one says that the limit exists, but the point doesn't exist. And that would be right here at x equals 5. Can you see x equals 5? That the limit, as I approach the left and the right, is the same y value. So the limit exists. Check. Oh, you know what? That's actually not a good example, because do you know what, Mr. Brown? Do you see how the point exists up here? Mr. Brown, that was a terrible idea. Let's not work at that one. Let's save that one for later. I was ahead of my time, friends. Let's instead look at x equals 5. All right, x equals 5. The limit from the left, limit from the right. Yay, checks. So step 1, does the limit exist? Check. Ooh, but step 2, where we have to check and see, does the point exist? No. The point does not exist, and there's not a dot anywhere else. It's an open circle, so the point does not exist. So we don't even have to do step 3 because step 2 is violated. It did not work. So there you go. That's one where the limit exists, but the point doesn't exist. Okay, for graph 2, I asked you to say, where does the point exist, but the limit does not exist? And that would be right here at x equals 3. Okay, x equals 3. Step 1, does the limit exist? Well, as I approach x equals 3 from the left, I get this value down here. As I approach from the right, I get this y value up here. Remember, it's what you get really, really close to. But so notice that the limit from the left and the right doesn't exist. Okay, that's cool. But do you notice the point does exist, and it's right down here, friends. At x equals 3, I get this y value here. So does the point exist? Yes, it does. Does the limit exist? No, it don't. So again, it's not continuous. And the last one, I asked you, can you find one where the limit exists, the point exists, but your answers are not the same? And that was x equals 5. Aha, that's what I meant to say. Here we go. Ready? Step 1. Does the limit exist? As you approach 5 from the left and the right. Let's see, I'm approaching from the left. It's this y value. As I approach from the right, it's this y value. So limit exists? Yes, sir. Does the point exist? Well, as I plug in 5 for x, where's your y value? It's here. It's here. I know there's an open circle here, but the point does exist. The y value is there. So does the point exist? Yes, sir. Last step. Is your answer from 1 and the answer from 2 the same? That's your question. Well, the limit from both sides was here. That's your limit. How about the point? When you plugged in the point, is that the same thing as the y value? No, that's up here. So you notice that the limit here on the bottom doesn't equal the point up here on top. So they're not equal. So even though you check step 1 and 2, that's great, but you have to check step 3 and make sure that the limit and the y value are the same. All right, let me erase all these markings, and let's just look at this graph one more time. And now let's just talk about the crude idea of, continuity. Watch, as I try to draw this graph with my pen. Do you notice I have to pick up my pen in order to make an open circle? I have to pick up my pen. Well, that breaks that sort of crude definition of continuity. So that guy's not continuous there. And I keep going. I'm going to keep drawing this graph, but, oh, wait. In order to get back up here, I'm going to have to pick up my pen. Darn it. In order to pick up my pen, is he continuous? No. As I keep going. All right, now, the point exists. He's just up here, but in order to draw that point, I'm going to have to pick up my pen and go up here and draw it, and then come back down here and draw it. So I had to pick up my pen. So is he continuous there? No. So 3 different examples. So it is really interesting that you check step 1, does the limit exist? Step 2, does the point exist? And step 3, are those two quantities equal? Okay, very, very important for continuity. So where is it not continuous? What we call discontinuities or discontinuous. A lot of you learned these last year if you were in a pre-calc honors class, but if you were in pre-calc regular, we didn't do this, but now is your chance to check it out. All right, well, this first one is awesome because you can see I can draw this graph very nicely, nice and smooth without picking up my pen. So, continuous, yay! Number 2, as I draw this one, I have to pick up my pen here in order to draw this one up here. So it's almost like I pulled out this point. He just got removed. Ooh, removed. Oh, he's called a removable. That's called a removable discontinuity, when you have a hole and sometimes you have a point, sometimes you don't. Because you look at number 3 over here, same idea, I have a hole, it's been removed, but there's no dot anywhere else. But he's still considered a removable discontinuity because I removed the point. Whether I removed him and actually placed him on the graph like on number 2 or not, I still removed him. So these both are called removable discontinuities. But what if I'm down here for number 4 and I'm drawing my graph? Okay, it's like I removed that point. Well, I kind of removed the point, but I didn't keep going from that spot. I actually had to pick up my pen and jump way up here. Oh, jump! Ah, this is called a jump discontinuity. So jump discontinuity is easy to see if you want to think about limits, because the limit from the left doesn't equal the limit from the right. It does for removables, but this one I just think about, I literally had to pick up my pen and jump up to this next branch of the graph. The last one is where you have to draw the graph, number 5 here. You draw the graph and you have to pick up your pen, but why? It's kind of like a jump, but because what's happening is you're just going off for EVs to infinity, and you approach another one from infinity as well. So imagine there being some kind of asymptote perhaps in between. So this kind of discontinuity where you pick up your pen again, because you're traveling over a vertical asymptote, is called infinite discontinuity, because you approach infinity from both sides of the asymptote. Okay, so keep those vocabulary words in your brain, because we'll have those on the AP as well. Don't worry about this section down here. We don't do the same for AP. But another thing you can do is you can also be just continuous from one side or the other. Not from left and right, but just one side. And that's okay too. For example, if you look at this graph here, this is the greatest interval or greatest integer function, or sometimes we call it a step graph. Do you notice that as I approach maybe from, let's see, if I approach 3 from the left, I get this y value. But as I approach x equals 3 from the right, I get this y value. So, okay, he's totally not continuous because the limits are not the same from left and right. But you know what, though? I feel like as I just approach 3 from the right-hand side, as I approach 3, I get this y value. Do you also notice that if I plugged in 3 to the function, actually the point is there too. So the limit from the right equals the actual y value as well. If that happens, if the limit from the right equals the y value, you have this. The limit from the right equals the actual y value. Then you are called continuous from the right. Okay, so all these graphs here look like they're continuous from the right. Versus if by chance, I'm going to cheat a little bit here, friends, don't tell anybody, but I'm going to put a dot here and I'm going to put an open circle here. Because to do that, now do you notice as I approach 0, let's approach 0, x equals 0 from the left. As I approach x equals 0 from the left, my limit is this y value down here. And if I actually plugged in 0 as my x, my y value would also be this same y value. So the limit from the left equals the actual y value. That means you'd be continuous from the left. This graph, unfortunately, though, as he is, as the greatest integer value or greatest integer function, is only continuous from the right. Because, in easier words, you're continuous from one side if the limit goes to the actual dot. If your limit goes to like an open circle, then he's not continuous from that side. So you can see as I approach from the left, on all these little branches, you're not continuous from the left because your limit from the left only equals an open circle and not a dot. But on all these, as I'm taking the limit from the right of each of these also equals the dot. So you're all continuous from the right. Okay? Great. So, okay, let's just take a summary right here. What is continuous? What graphs do we have continuous? You know so many graphs now at the sort of the pinnacle of your high school math career. So which ones are continuous? In general, pretty much all polynomials are continuous everywhere. All of our polynomial graphs, like x cubed, x to the fourth, x to the fifth, they're all smooth. You can draw them without picking up your pen. Check. Rational functions. Rational functions are the ones that sort of look like these, sort of the reciprocal type functions as well. Those are also continuous, but only on the parts where you're drawing them. Not all the way, and you can see because of this asymptote, I'm not continuous there, but on the parts of its domain, sure, like this part's continuous, and this part's continuous. So I'm going to say rational functions are continuous, but only on their individual domains. And therefore, we can also say the same thing for root functions. You know, for example, a square root function It's continuous for its own section that it's drawn, but it's not continuous over here because it don't exist over there. But for the part that you do draw, it is continuous. Same thing for inverse and just regular trig graphs. It's continuous on its own domains, exponentials, and log functions as well. Okay, so in general, most graphs are continuous, especially if they're polynomials, but for the ones that are not always continuous everywhere, they're continuous on their respective domains, and so we're safe for that. This is a very, very important theorem in calculus, and it's on the AP test every year. But in fact, I do want to come back to it later on a separate video because I want to spend most of the video talking about it because it's a big one. It's going to take a lot of writing. We're going to actually have to prove that things follow the IVT or the intermediate value theorem by writing sort of a mini paragraph. Writing on the AP test? Boo. But we'll practice that a bit. So I'll save that for next time. So skippity skip skip. And let me give you a final thought here before we call it quits. Can we talk about piecewise functions? On functions that are made up of pieces like you see here, where are they continuous? First of all, I think we have to get an idea of what does this look like? Because it's not continuous because it's made up of pieces, I don't think. I don't know. Let's just imagine what this graph looks like. So a typical piecewise function, this one here. All right, when x equals 2, I get the y value of 1. So over here, I get 2, 1. Great. But for the whole rest of the graph, when x is not 2, I'm doing this, which is probably hard to know what this is, but it's actually just a line if we think about it. So this is just a line that looks sort of like this. But because of the vertical line test, I need to have an open circle over here. So this is probably what our graph looks like. For when x equals 2, I have a dot. And for everywhere else on the graph, I have just a line. So can you see that this is not continuous, and specifically, this is a removable discontinuity. So where is it continuous? Well, almost everywhere, except pretty much where x equals 2. But let's check. Let's check and see. So what we're going to do is to check continuity. Remember, we've got 3 steps here, right, friends? We're going to do 1, 2, and 3. Let's check the limits. Remember the limits from the left and limits from the right, and see if they're equal. See if we hit the same number. Ready? Let's go to our graph over here. As I approach x equals 2, and you're going to choose 2 because it's over here in the domain. That's sort of our breaking point. That's where something different happens. So 2 is sort of our center of our focus. So let's check 2. When I approach 2 from the left and 2 from the right, I do get the same number. What is it actually? As I approach 2 from the left and the right, well, let's see. If I plugged in 2 over here, what is my y value? Ooh, do you see that we're trapped down here in the denominator? But that's okay. Remember, you guys know what to do. After you plug it in, if it doesn't work, we got to do a little bit of algebra magic, which means I can factor the top. Great. So they cancel, get out, and now I'm just trying to figure out what's the limit as x approaches 2 of just x plus 1. Great. Can I plug that one in now? Yes, I can. And I get 3. Okay, so this y value up here, where the open circle is at 3. So the limit from the left is 3. The limit from the right is 3. Are they equal? Yes, sir. So my limit from the left and the right is 3. Great. So the limit exists. Good. Continuity. Check 2. Ready? What is the actual y value? When I plug in 3, what is f of, when I plug in 2, that's our breaking point here. When I plug in 2 here on the graph, what's my y value? Oh, wait. It's 1, right? So when I plug in y value, plug in my x value of 2, I get 1. Okay, so, but the point is, though, the point exists. So check for step 2. Remember, step 2 just says, does the point exist? Yes, we have a dot over here. That's happy. But remember, for step 3, we need to check and see, does the limit from step 1 equal the y value of the point in step 2? And no, they don't. So even though the limit exists up here, the point exists in step 2, they're not the same. So is it continuous? No. So where was it discontinuous? The answer is at x equals 2. Okay? So it's really important. Every time we talk about discontinuity, especially on the AP exam, we do have to go through all 3 steps and check and see. That ends with a beautiful AP question. I love this multiple choice question. It's on there almost every year. And it's usually a 2-minute question, but there's a bit of algebra here. Question says, for what value is C if this graph, this piecewise graph of f of x, is actually continuous everywhere? So we want this graph to be continuous. what does c have to be equal to? Okay, go ahead and pause the video and just play with it a little bit. Try the 3 steps for continuity and see what you can do and see if you can solve for c. If you're totally confused, take a pause for a minute and then I'll walk you through in just a sec. All right, friends, so let's take all 3 steps. Ready? To check and see what c is, I first need to make sure this is continuous. So our breaking point here, again, this is where the domain changes, is at x equals 2. So that's going to be sort of our discontinuity or continuity area. So at x equals 2, something changes. I go from this branch to this branch. We just got to make sure they connect and make it continuous. Okay, so I want to make sure the limit from the left equals the limit from the right. In order for that to happen, let's check the limit from the left. As x approaches 2 from the left. Remember we learned last time, the limit from the left, I want to do the left of 2. That means where x is less than 2. So I'm going to look at branch number 1, the first equation. All right, well, let's plug in 2. So as I approach 2 from the left of my function, that should be cx squared plus 2x when x equals 2. So I'll put c times 2 squared plus 2 times 2. And that's 4c plus 4. Great, that's my limit from the left. Awesome. No idea what to do with that yet, but no worries. Hang on tight. Let's check the limit from the right. The limit, as x approaches 2 from the right of my function. Okay, remember over here, guys, when you take the limit from the right, that's where you're to the right of 2 or greater than 2. So I'll use this bottom equation here. Okay, well, I'm going to use this equation of x cubed minus cx when x equals, again, 2, because I'm plugging in the value of 2. That would be 2 cubed minus c times 2. That's 8 minus 2c. All right, now, in order for the limit to exist, do you agree here, are you a believer, that this value, whatever it is, has to equal this value? They have to be for the limit to exist. Okay, cool. Well, we're going to do that in just a second. We're going to set them equal to each other and see what c is to make it work. But let's just check the rest of our continuity. For step 2, we need to see, does the point exist? And if you look up on our graph, when x equals 2, is there an actual y value? And the y value would be, using this second equation, because this has the equal sign for 2, the y value would be this. Okay, cool. Well, if that's our y value, we've already tested it here from the limit. So when we use this later for our limit, the point will exist. When I plug in x, because it's equal to, I am plugging it into a function, so I should get a y value out. So for step 2, it is going to work. The point will exist. Now for step 3, to check and see, does the point value from step 2 equal the limit from step 1? Well, the limit's going to exist in a second, because we're going to check that right here, friends, in a minute. So the limit hopefully will exist. The point in step 2 are exist. Now, do we know if they're equal to? Well, if you think about it, the point value, we're going to plug into this equation, right? Because that's where x is greater than or equal to 2. But I'm using that, again, also here for the limits. So the limit equation is going to be the same as the point equation. So yes, the point will eventually equal the limit. It will work. Okay, so we're sort of doing a little bit extra work for this question. It's going to take a little bit longer for 2 minutes. So if it's okay with you, can we just stop here at step 1 and just say, all right, let's just check if the limit from the left and the right are equal and solve for c? Yes, that is actually okay. You don't have to necessarily go through step 2 and step 3 as well to prove it. And knowing that we're sort of short on time on the AP, it's okay to just check the left and the right limit. Okay, so the point is, I'm going to erase all step 2 and all step 3. Let's just use step 1 to solve for c and walk away. But I just wanted to show you why step 2 and step 3 are kind of important for continuity and for good practice. All right, so let's check. This is the limit from the left. This is the limit from the right. And in order for the limit to exist, they have to be equal. So let's just solve. All right, let's just do a little bit of algebra here. You move some furniture around, you solve for c, and I think you get something like, what, 4 over 6? Is that right? I think that's about right. Or 2/3. Cool, that's what c equals. And you can walk away. This would probably be a multiple choice question, so the choices would be there and you would see 2/3. But again, just for the sake of it, let's say you had a little bit extra time. Let's see if this actually works. Ready? Let's put 2/3 back in here. That means this equation here would be 2/3 for c, x squared plus 2x. The bottom here would be x cubed minus 2/3 x. Let's just check and see if it works. If we plug in 2 on the top and plug in 2 on the bottom, would I get the same y value? Would I get the same limit? Let's check. Ready? Okay. When x equals 2, from the left, I get 2/3 x is 2 plus 2 times 2. Over here on the right, if I plug in from the right, I should get x is 2, right? So 2 cubed minus 2/3 was the c value times 2. All right, let's go up and simplify this guy. In the purple, I would get 2 squared is 4 times 2, 8/3 on the bottom, plus 4. Oh, common denominator, ready? I think that's about 20/3, doing some quick math there. All right, down here in the red. So that was the left. From the right, I would get 2 cubed is 8, minus 2/3 times 2 is 4/3. All right, common denominator, and I would get 24 minus 24 minus 4 is 20/3. And look at that. Do you notice that the limit from the left equals the limit from the right? And if you actually did plug in 2, you'd have to plug into the second equation, which means you'd also get 20/30, which means the point exists, which means the point equals the limit, so he's continuous. Yay! And we were all rejoicing. So again, this is a great AP question where basically what you're going to do is you're going to just look at step 1 and plug in 2 to the left, first equation, 2 from the right, second equation, and set them equal to each other here, guys. Good work today. That's the end of continuity as we know it. We'll come back and do that IVT, intermediate value theorem, and save that for another video. See you all later.